Hello and welcome to this video. My name is Christian Krabenhoft and I am speaking from the University of Liverpool in the beautiful city of Liverpool, England. I've even had to draw my curtains because the sun is just blazing in. This video will introduce our new program OPTUM G3. To give a very brief introduction to it, a sort of getting started manual. We'll solve a few very simple problems, but I won't go into any real detail about the underlying computational technology, the types of finite elements we have, the models we have, and so forth. It's going to be very simple and very basic, more of a getting started demonstration video. So when you start up the program OPTUM G3, this is what you see, and for those of you who know G2, you'll hopefully see that it sort of is kind of similar in a way, or in many ways, and it's supposed to be similar. We have the ribbon up here with these different tabs, geometry, where we have tools for defining and manipulating geometry, materials, features. You'll see some of the features, some of the loads here are grayed out. I'll return to why that is in the course of the video. And then results, which at the moment is empty. So that's the ribbons, and then you have what we call the canvas, the big part here where you define, create the geometry, and then over you'll see, this is quite important, the coordinate system down here, the global coordinate system X, Y, Z. That can be quite important from time to time to really sort of pay attention to that. We have the possibility also of using local coordinate systems, but I think I don't think I'll get into that aspect of the solid modeling in this presentation. It's going to be pretty straightforward. And then, so that's the canvas, and then the stage manager over here, which we have in G2 of course as well. The analysis, the stages, the analysis type, and down here the some settings, the type of elements, the number of elements, measured activity, yes, no, and so forth. So the problem I am going to solve today is that of a circular foundation on first a Tresca soil, so an undrained total stress analysis. I'm going to find the bearing capacity, and then I am probably going to solve another couple of problems, variants of that problem of a circular foundation on a large soil domain. So let's get started. We first need to define the soil, and I'll do that using this so-called box tool up here. So I click that, and then I am supposed to select a point, one point for the base of the box and another point. So I'll make this base 15 by 15. So this is 0.0, and this is then 15 out in the X and Y. See the X and Y directions, and then I'll define that point and then define a height, and I'll make that 10 and zoom all. So here I have a box, I can select it, and but there's not much point in that right now. Then I want to of course define the foundation on top of the box, and I'm going to model 1/4 of the problem. So I'm going to put the foundation here at this point. So 3/4 of the foundation will not be modeled. Only this 1/4 that rests on the domain in here will be modeled. Now for that, for modeling that foundation, I can use either a cylinder, that's somehow the obvious choice, or a so-called end prism, which is in many ways somewhat more reliable because you can control manually the number of subdivisions in the cylinder. So it's a discrete cylinder with a user-defined number of subdivisions. So I'll select that, and n is the number of subdivisions, the number of sides in this discrete cylinder. I will choose 40 here because we only actually need 1/4 of it. So the quarter we have will have 10 sides, which approximates a quarter circle fairly well. Position here, radius, I will select a radius of say 2, and a height I can make that, let's make it 1. Okay, so I now have the soil and the foundation, except that 3/4 of the foundation is sort of sticking out, and I need to get rid of that. So how do I do that? And that can be done in various ways. What I'm going to do here is I am going to draw another 2 boxes like so and like so, and these boxes then intersect with the foundation. You can see it here. So the foundation has been automatically partitioned. As in G2 we have automatic recognition of intersections, both between solids, between surfaces, and between lines. So this is quite useful, and it's a sort of a quick way of modeling this problem. So I select these boxes, and then you see I have 4 parts, and I can select 3 of them, and I'm left with exactly what I want. So now assign material properties. So we have the material called Tresca, as in G2. It has an unrange history. The default value is 100. We can change that, or we can leave it as it is. I think we just leave it as it is. And then the foundation, and as in G2 we have the rigid material. So it's a rigid, perfectly rigid material with the default unit weight is 0, and let's just leave it at that so we can compare with an invisible solution. So it's a kind of, say, academic foundation. Now, when I click on these solids here, well, the solids are selected. If I click on a line, it's not so easy like that. I'm not sure you can see it. The line is selected, or a point is selected. I can select a point as well, I think, like that, yeah. And you could, in principle, change the coordinates over here, just as in G2. But I want to, what I would like to do is select this surface up here and then apply a uniform load on the surface. And in order to do that, I need to disable solid selection, because if I click here, the whole foundation, the whole solid is going to be selected. So I untick solid up here, and I can then basically select the surface. And if you look at features, so it's a multiplier distributed load, just as in G2, or the equivalent of the G2 multiplier distributed load that I want to apply. And you can see it's grayed out, it's grayed here, but if I select the surface, well, it becomes possible to select, and I'll do like that. And if you zoom in, you can see that it is actually a uniformly distributed load over the surface of the foundation. So, and then as in G2 as well, standard fixities, that's a button you click, and then relevant boundary conditions for this example are applied automatically. So normal boundaries, normal supports here on the on these sides and up here as well, and then the bottom of the box is fully supported. I should say as well, I completely forgot that, but better late than never. 2 important buttons, keyboard shortcuts that are relevant to know, that you need to know, are control. So control, and then moving the mouse rotates the solid, and shift pans. Control and shift really takes care of everything you need. If you have a wheel on your mouse, you can also zoom in and out using that wheel. That's something I would highly recommend. If you don't have it, then get a mouse with a sort of a scroll wheel on it. I think that also you can also rotate it. Use that. If you can click this wheel, you can rotate it. So you don't actually need to use the keyboard very much. But so that's how it is. And we are then ready to solve this problem. And we're going to do a limit analysis, and we are going to use, we have a choice of elements. In this case, and these elements are lower, upper, and mixed. So the lower and upper give up lower and upper bounds. I will not use those in this video, but I'll simply use the so-called mixed element. This is an element that incorporates features from both the upper and lower bound formulations to get an element that produces not strict upper or strict lower bounds, but produces results that are somewhere in between, and a lot of the time actually very close to the exact solution. So this is a very, very good element, very accurate element, and usually you don't need very many of them in order to get really quite accurate results, especially if you use mesh adaptivity, which is something I really recommend. So that works as in 3D, as in G2 as well. So you say yes, I want mesh adaptivity, the number of adaptive iterations, so the number of solves you'll do basically in a run 3, that's the default in G2 as well, and then the start elements, let's just leave that at 1000. So basically we create a uniform mesh first, solve the problem, that's the first iteration. Then in the next iteration we adapt the mesh to the solution, and then we do that one more time, a final and third time, and then let's see what happens. So I press here, and that kind of looks like G2 as well. And the thing is, of course, 3D is always going to be a lot more demanding in terms of computational time than 2D. That's why we have made an effort both to really have very accurate finite elements. So for most problems, I would say you don't really need a huge number of elements, and also we made quite an effort with respect to mesh adaptivity. So that combination, accurate elements and mesh adaptivity, really makes it possible to get really quite accurate solutions in a fairly limited amount of time. So the solution is out now. The collapse multiplier is 618, and how good is that solution? Well, and we can see how we can plot the shear dissipation, and you can see it sort of looks as expected, I would say. Right, and how good is that solution? Well, the on-range shear strength was 100 kPa, and I know that the exact solution in terms of the maximum, the ultimate stress on the foundation is 6.05 times SU. So that's 605, and we have a solution of 618. So that's really not, so let's say 618 minus 605 divided by 605 times 100. So an error of 2% for this problem using 1000 elements. Of course, you use more elements, you get the error even smaller, but this is really quite a good, quite an acceptable level of accuracy, I think. Then what is often the case with sort of clay deposits, there's often a variation of shear strength with depth. So that is to say an increase of shear strength with depth, and we can account for that as well in this program, just as in G2, and I'll just show you how to do that. So what we need is the coordinate, the Z coordinate of the top part up here, and if I select a point here, I can see that Z coordinate is 10. Okay, let's then try to see if we can get a gradient up and running. So I select the parameter that I want to specify an increase with depth for, and I press this P for parameter. And I move to gradient, and there is something called value. That's basically the value of the parameter, in this case the under-range shear strength, at the reference point, the Z ref here. And I'll pick a Z ref of 10, and then the value up here at the surface, I could make that quite small. Let's make that 5, and then a gradient of say minus 5. So, and it needs to be minus because it's downwards. If you look at the Z coordinate here, so it's an increase with in the opposite direction of the Z coordinate. So 5 kPa increase per meter. So at the bottom here, so this is 10 high, so at the bottom here I should have a shear strength of 55. So it varies between 5 up here and 55 down here at the bottom of the box. Let's see. So, and you can see as well that we have then not one material parameter, not one number shown, but this sort of a gradient indicating that we have specified something other than just a constant value. And meanwhile, while this is solving, I will start up the well-known program ABC, Analysis of Bearing Capacity, by Chris Martin from Oxford University. So it's a very simple app. It's based on the method of characteristics, and it gives very accurate results for a central uniform loading of both strip and circular foundations. And it allows us to basically solve this problem as well. So C0, that is, in this case, is 5. That's the under-range shear strength at the top of the soil layer, at the level of the foundation, basically. K is the gradient, and that was 5. It's minus 5 in Optum, but it's 5 here in ABC. 0 friction, and the unit weight here, I believe, is 18. I think. Let's just check. Yes, so the unit weight is 18, and it's a circular, and it's a rough, and B, so the half width was 2, so B is 4, and there's no surcharge. And then let's have an auto guess, and then let's double up. So according to ABC, the alternate stress QU 43.7, and what do we get from Optum? So that's 40. Let's just copy that. And what do we get from Optum? Well, we get 44.8 something. So actually, in this case, again, we are slightly above the exact solution. We can regard the ABC solution as the exact solution. So let's see what the error is. I think it's again something like a couple of percent, a little over 2%. Again, that's a pretty good accuracy. And you can see as well probably that the failure mechanism is slightly shallower than in the case where the under-range shear strength is just constant. So there's a tendency to keep the failure, of course, as shallow as possible, since the variation, and we can plot that over here as well, is such that we have an increase of strength with depth. So from 5 up here at the top surface at the level of foundation to 55 kPa down here at the bottom of the box. So that's how that works, and I will just one more example, and I will now move to a drained analysis, sand, and I will use one of these material, standard default material, just as in G2 we call a loose sand MC. So that's a sand modeled as a more Coulomb material with a friction angle of 30, a unit weight of 16, and again these parameters can be changed, but again I'll leave them as they are. And then also, just to demonstrate another feature, we can of course have surcharge. So let's put some surcharge, basically some fixed distributed load on the surface here, and let's make that 10 kPa. And then let's try to solve that problem. And meanwhile, I am going to switch back to ABC and set the problem up. So 0 cohesion, no variation, friction angle of 30, unit weight of 16, and a surcharge of 10. And let's see what ABC gives us for that. A little over 1,000, 1,022.5. And if we look at what Optum has given us so far, it's actually not that far from, well, we can call this almost the exact solution. It's really not too far from it. Let's copy that. So Optum gives 966, ABC gave 1022, 23, and error of 5.5%. So a bit more than twice as much roughly as in the undrained case, and that's not really unexpected. And there is of course also, as our friends in Sheffield limit state have pointed out, and often do point out, and I think rightly so, one possibility is to measure the error with respect to the actual final limit load. Another possibility is to measure the error with respect to the input, with respect to the friction angle. So in this case, the exact solution is 1022.54, and we get actually this, in this case, notice that something slightly below 966. So the question is, what friction angle does this 966 correspond to? And we can and that'll be something very close to 30, probably something like 29.7. Yeah, something like that. So the error, yes, it's 5% in terms of the limit load. In terms of the friction angle, the error we make is 0.3 degrees. So again, a very accurate, and actually you could argue in many ways more accurate solution than the ones we found in the undrained case with the Tresca material. So let's just have a look at the shear dissipation. Yes, the mechanism is a greater extent than in the undrained case. That's kind of expected, and it looks like this. So that was a brief getting started introduction to Optum G3. If you have any questions, please do get in touch, and I'll continue to post videos on more concrete applications. I'll also have a video explaining some of the advances we've made with the elements, with both the upper and lower bound elements, and also this mixed element, which is, as you can hopefully see, really quite accurate. So see you next time.